video 2 for P2, forces of motion. Newton's third law says that every action has an equal and opposite reaction. So if we take that first picture of you looking really confused next to your computer screen, so what forces are acting on you in the chair? So your weight is pushing down on the chair. Remember, what is that force called that is pushing upwards on you? It's called the normal contact force. And which force is bigger? Well, they must be the same size, because if one force was bigger, if your weight was bigger, you would accelerate downwards towards the ground. And if the normal contact force was bigger, you'd be flying up in the air. But that's not happening. So every action has an equal and opposite reaction. If we look at Zlatan Ibrahimovic heading that football, which force is bigger? The force of the ball on his head or the force of his head on the ball? Which force is bigger? Well, they're the same size. So when forces interact, they are always the same size as each other. And I'm going to go into this in more detail on the higher video. So why that is on the higher video only. If you are doing the foundation, but you want to push yourself, please watch that video and listen to my explanation of why this is. But if you're happy, just remember that if something is on a surface, their weight is equal to the force that that surface is pushing back on them. Or if a car crashes into a wall, the car will put as much force on the wall as the wall does on the car, as we will see in the last thing we're going to look at in this video, which is about car crashes. The next thing that you need to know is stopping distances. And stopping distance is made up of a thinking distance and a braking distance, which I will describe in a second. If you want to learn to drive, you will need to remember these stopping distances at various speeds as found in the highway code. So this will be part of your theory driving test. And what you'll notice if you look at these closely is that the faster a car is travelling, the further it travels as it stops. So if a car is travelling at 70 miles an hour, it will require a total of 96 metres before it comes to a stop. So that's probably something like Mr. Ord's classroom down at the PE changing rooms. But if a car's travelling less fast, it doesn't need as big a distance to come to a stop. So we're going to look at stopping distance in a little bit more detail here. So this starts when a hazard happens. So if somebody walks onto the road, for example, or an animal runs out onto the road. So the thinking distance is the distance that you travel between seeing the hazard and pressing the brake. So it is because of your reaction time, and the faster you're travelling, the thinking distance will also increase. And the reason why the thinking distance would increase if the speed increases is because distance equals speed times time. So if the speed increases and the reaction time stays the same, the distance will also increase proportional to the speed. And things that would affect your thinking distance include drugs such as alcohol, the amount of sleep you've had, or distractions in the car. And it's important to point out here that alcohol would actually increase the thinking distance, and that is because your reaction time would be longer. So the amount of time between seeing something and pressing the brake pedal would also increase. So your alcohol increases the thinking distance. Normally increasing things mean that they're better, but in terms of thinking distance, a shorter thinking distance is better for stopping the car quicker. And the next thing is the braking distance. The braking distance starts when the brake is being pressed, and it would finish when the car has come to a stop. Now, for the students trying to push themselves for higher grades, the kinetic energy equation, which we'll look at in physics topic 3, is kinetic energy equals half mass times velocity squared. And what has to happen when a car brakes, it has to turn that kinetic energy into other forms of energy. So in the brakes, it takes that kinetic energy, the movement energy in the car, and it turns that into thermal energy. And because this equation has velocity squared, velocity times itself, if a car is going twice as fast, 2 times faster, the amount of kinetic energy it has is 4 times greater. So if we look at this, it is not directly proportional. As a car gets faster, its braking distance goes up exponentially. And if we think about things that would affect the braking distance, this would include things such as how new the brake pads are, the condition of the road, is it wet or icy, or is it nice and dry? And another one is the mass of the car. So heavier things such as trucks, they have more kinetic energy, and they need to get rid of more kinetic energy because they are heavier. So things that are heavier would have longer braking distances, so it would be more difficult for a car to stop if it had more passengers. So remember that the thinking distance is the distance that a car travels between seeing a hazard and hitting the brakes, and the braking distance is between hitting the brakes and the car coming to a stop, and altogether that is the stopping distance. So stopping distance equals thinking distance plus braking distance. And the final part of this course that everybody needs to know is to do with car collisions. And the main thing that you need to remember here is the faster that you stop, the more you decelerate, the bigger the force. And that's because the car needs to lose its kinetic energy. And if a car is going faster, it has more kinetic energy that it needs to get rid of. And if you are in a collision in a car that is going faster, that energy can do harm to you. So we need to think about different safety features that cars have, which reduces the impact on the passengers. And the first thing is crumple zones. And if you look at how cars are designed, they have a hard shell, which is where the passengers sit, but the front of the car is made out of softer metals, such as aluminium, and they also have the nice squashy rubber tyres. And this acts like a spring, and this reduces the force on the passenger. So if we imagine a car that didn't have a crumple zone, if the front of the car was hard, as soon as it hit a wall, that car would stop immediately. And if it stops really fast, the force is going to be big. What the crumple zone does is it increases the amount of time that the car is slowing down. So if the same car has a soft front, as soon as it hits the wall, it's going to be putting a force on the car to slow it down. And as that wall gets closer to the passenger, it will continue to put a force on the car, but over a longer time. So it stops more gradually, so the force is reduced. It's less on the passengers. And don't try this at home, but if you fell out the second floor of a house and you hit concrete, you would stop really, really quickly onto that concrete. If you landed on a mattress which has springs in, you would hit the mattress first and then continue to move down towards the concrete. So you are slowing down over a longer time, which reduces the force on you. And you would instinctively know that it's going to be easier and softer falling on a mattress than it would on a hard concrete floor. And this is kind of what the crumple zone is doing in a car. It is increasing the amount of time over which the car slows down to reduce the force on the passenger. And that is also what the airbag does. So if a person hits an airbag, their head's going to slow down over a longer period of time, and it's going to be much better for them hitting an airbag than it would be for them to hit the dashboard, which is made out of hard plastic. And all that a seatbelt does is it allows the person to slow down with the car. If somebody was not wearing a seatbelt and they were travelling at 20 meters per second in the car, if the car crashes and slows down to 0 meters a second, that person is still effectively going at 20 meters per second because they were going at the same speed as the car. So if they come to if they crash and the speed of the car slows down, they are still going at that speed and they will hit whichever object is in front of them at that speed. So if that is the dashboard, they're going to slow down really, really quickly and have a massive force on them, which could kill them. But the seatbelt allows the passenger to slow down gradually and take advantage of the other safety features of the car, such as the crumple zone and of the airbags. So one last way of looking at this. So we've got a car there and it's moving to the right at 30 meters per second. There's some shopping on the back seat and the person in the front has their seatbelt on. What's going to happen if this car crashes? Well, the thing that they crash into will put a force on the car. Which force do you think is bigger, the force of the wall on the car or the force of the car on the wall? They're the same because of Newton's third law. What's going to happen to the speed of the car as it crashes? It is going to decelerate, and that deceleration equals the force of the wall divided by the mass of the car, which is Newton's second law. So what is going to feel a bigger force, the shopping or the person who is wearing a seatbelt? Well, because the person's wearing a seatbelt, they're going to take advantage of the crumple zone on the car and of the airbag, so they're going to slow down gradually and they would feel less force. The carrier bag, however, is still moving at the same speed that the car was, so it is going to hit the seat in front and it is going to slow down quickly, leading to a much bigger force. So please, if you're doing the standard paper, try some questions now. Log on to the VLE, download the question paper, try it as hard as you can, and then also download the mark scheme and mark your own. There's a link in the description to the correct VLE page. If you're doing the higher course or the triple course, you have additional videos to watch. The next one's a higher video, so click the link. Thanks for watching. Good luck for your up and coming test. Cheers.